Okay, so in the last class we were discussing the transmit equalizer and some of the circuit design details of it. We make the transmit equalizer by connecting a number of differential pairs in parallel, and we were looking at how to get variable coefficients. There could be other ways, but the easiest way seems to be to vary the tail current. That's why the amount of current you switch varies. So the weightage of each bit can vary. So if you have different currents in different taps, that gives you different tap weights. Okay. Again, there are probably innumerable ways of varying the current source, but we are discussing one particular kind where we can vary it digitally. Okay. We have a number of current cells in parallel and we turn it on and off. But of course, you can think of varying the gate voltage or doing something else. Okay. And one constraint that we would like to maintain is to maintain this node capacitance to be as small as possible. I'll explain that shortly why that should be the case. But if you want to keep it as small as possible, the best thing is not to split this current source, but you have the reference device, and the current that you get is the reference current times the ratio of the aspect ratios. Okay, so you either vary this width or this width, you get the same effect as far as the current bias is concerned. Okay, so it may be preferable to vary this or effectively vary this current source in order to get varying tap weight. And we also saw that anytime we have a transistor like this, we can switch number of transistors either by switching the gate or switching the source, and we can do the same thing on the reference branch as well. Okay. So let's say I choose to switch at the gate, and I'll show 3 levels, and this goes to the biasing current source. So this entire thing is the reference branch. So depending on whether the gate is connected to its drain or ground, the transistors will be active or not. So if you have the smallest transistor on this side, you get the largest current multiplication, and if you have all transistors connected, you get the smallest current. And all 3 transistors here, let's say M, A, B and C, they don't have to be equal. You can make it in factors of 2 or something, so that you can also get binary weighted weights. Okay, so with different switch combinations, you can get different weights. So this is the idea. That way, the whole point of doing something like this is to keep the tail node of the differential pair as compact and low capacitance as possible. Okay, switch the reference branch from which gate? Oh, here. Yeah, if everything is switched off, then if all transistors are switched off, then we would like to not have this node floating like this. So we should have it to ground. That's correct. What happens if I don't have the switch? Yeah, actually this current source will pump into an almost open circuit and pull this node up to VDD. Okay, so then you get a large current. So we want to not have that case, so we should have a shorting switch to ground. So in practice, what we do is we turn off this current source also if we want to turn off everything. Okay, let's take a look at why the tail node capacitance is a problem. Let's say we have a differential pair and we have a capacitance from tail node to ground. What is the effect of that? What is the effect of the tail node capacitance? What happens to the current? Okay, if there is switching, what happens? It won't vary very fast. Okay. So yeah, all that is true. It's actually hard to analyze a dynamical nonlinear circuit like this. So first what we'll do is, let's take a case without the capacitance and then say that Vp and Vn vary this way. Okay. So basically they have some switching waveforms. So this is, let's say, Vn and Vp. What does V tail look like? Will it be constant throughout? Yeah, this is at its minimum when Vn equals Vp. Is that known? So if you plot this V tail versus Vp minus Vn, it will, depending on the common mode voltage of Vp plus Vp and Vn, it will have some even characteristic like this. Okay, and this point is at the common mode of Vp minus one threshold voltage minus the overdrive of this transistor when it is carrying a current of I0 by 2. So this is what it looks like, and if it is switched completely to one side, then if this is off, let's say, between Vp and Vtail it's a source follower, so it will keep increasing with Vp if one side is completely switched off. So it has its minimum value when Vp equals Vn. So Vtail may do something of this sort. Okay. So without capacitance, that's what it does. So to make the analysis easy, what we'll do is we'll have a small capacitance. We'll connect a small capacitance to this node. Assume that the voltage waveform has not changed substantially, and see what happens to the current. Okay. So of course this the transistor is still behaving like current source of I0. What will be the current through IC? So it will be C times the derivative of this V tail. So does something like this. It is 0 when the voltages are steady, the current through the capacitor. Then it has a negative current, that is current is flowing back this way, and then it has a positive current. Okay. So it depends on this derivative. When the voltage is decreasing, it has a negative current. When the voltage is increasing, it has a positive current. Of course. But note that this is an approximation. We have taken the same value of V tail as would appear when there is no capacitance, and doing the analysis based on that. So this is IC. So what does this mean? So the tail current will be this plus the constant current I0. So the tail current also does something like this. What will it do to the waveforms at the output? In response to this Vp minus Vn, I should get a Vop minus Von, which is, let's say, like this. What will I get in presence of the capacitor? When it starts falling, there will be an increase and then something like this. Is that correct? Say this is some nonlinear dynamical circuit. If you try to apply the equations and try to solve it, it's almost impossible. So you have to have some kind of intuitive heuristical way of solving this. So how would you go about solving something like this? Again, I'm not interested in the exact numbers that probably you can get from the simulator, but when you look at something like this, you should have an idea of what happens, right? So what will the output look like? The current is affected, yes. It says a current source is in common mode, output is differential, so the output is not affected. Is that correct? There should be a variation. Why? Yeah, the total current is now varying. Okay. So what happens is you can think of it as the current is the ideal value. For a while it is less than what it's supposed to be, and for a while it's more than what it's supposed to be, and then it comes back to the normal value. Okay. Let's take an unrealistic case where the current in fact does something like this. So this is the tail current of some differential pair. What do you expect the output waveforms to be in this case? How would you construct the output differential waveform here? So I am saying the tail current of the differential pair happens to look like this. How it came about, let's not worry about. And of course, such abrupt transitions are in reality not possible. But so actually the output is simply a scaled version of the current, right? The output current of the differential pair depends on I tail. So, and that goes into some fixed resistor, so the voltage also is directly proportional to I tail, you can say. I mean, there is some nonlinearity involved, but the swings are directly proportional to I tail. So, for the ideal value of current, perhaps the output would look like this. For the smaller value, it may have looked like this, and for the larger value, it may have looked something like this. So if the current does switch this way, then you can see that it follows the ideal value up to here, and the smaller one up to here, and the larger one up to here, and the normal one after that. Of course, in reality, that's not what you see, because everything is smooth, and this is a very, very crude approximation to what happens. So in reality, if this was the ideal output, what you see is that before the transition, you see less than what you should, and after the transition, you see more than what you should, and then you can have something of this sort. So it's not like symmetrical on the positive and the negative side. So before the transition, when the tail current is reducing, you see less than what you would normally see, and after the transition, when the tail current goes beyond the steady state current, you see more than what you see. That's what you are seeing here. Okay, more meaning in magnitude. So the black curve is what you would see normally, and the red is what you see in presence of the tail node capacitance. Is that convincing? So, and you can do this simulation and confirm that this is in fact the case. as the capacitance value increases, even this approximation breaks down, but you will see some waveform that is non-linearly related to the ideal output waveform. So what happens is the response will be non-linear. We wanted to make a linear equalizer, but it becomes non-linear. How do you say it is non-linear? Is it non-linear or not? How do you figure out? Because even if you pass a pulse or a step through a linear filter, you can get waveforms which do various things. Okay? How do you distinguish between a linear case and a non-linear case? We are of course using the non-linearity in a certain way. So this is true. If you double the input, if you see double the value, that is a measure of linearity. But that test you can't apply. In this case, you are using some non-linear elements to realize a linear transfer function. Okay? It's not as though it is continuously linear. You are using in fact a differential pair in a switched fashion. So if you double the input, you don't see anything. So you make a positive transition and a negative transition, and the sum of the two should be 0 if the response was linear. Okay? And this is a realistic case, because this is something that you will see. If the bit was 1, you will see the transition going one way. If the bit was -1, you will see the transition going the other way. And the two should exactly cancel if the response was linear. Is this okay? So does it cancel? Does it cancel or not? So a negative going ideal transition is like this. Doesn't look symmetric, but imagine that it is symmetric. And a positive going one ideal transition is like this, and the sum of the two is 0. Okay? What happens with the tail node capacitance is, this becomes smaller in magnitude here and larger in magnitude here, and the other one also becomes smaller in magnitude. Actually it does sum up to 0, right? Does it or does it not? So if you look at the differential waveform, it looks symmetric, but then you have to also keep in mind that this has a lot of approximations and things will not be exactly symmetric. Okay. So what happens is, if you look at the differential waveform, they do sum up to 0, because you do get like the positive one in one case and the negative one in the other case. So it does sum to 0. But if you look at each of the single-ended waveforms, that will be non-linear. Okay. So that will look different for rising case and the falling case. Okay. So if you look at each of these currents, so again, for the ideal case, they will look like this. And for the non-ideal case, here the current is smaller, and here it is larger and it does something, and here it is smaller and larger and does something of the sort. So the falling transition is different from the rising transition, isn't it? If you look at each of the single-ended currents, falling a 1 to 0 transition will look like this, and a 0 to 1 transition will look like this. But they should look opposite of each other if it's a linear case. So the single-ended waveforms are non-linear. The differentially, ideally, it looks like they will cancel out, but in reality, it will also not cancel out very well. And also, in case of an equalizer, you will be summing the outputs of many taps, all of which have different weights. Okay, some of them will be rising, some of them will be falling. So you will be summing a whole number of things, and the result may or may not be linearly related to the input. Okay, depending on the weights. But if you look at the single-ended waveforms, they will definitely be non-linearly related, because this is the response to a negative step and this is the response to a positive step, and they don't look anything like each other. So, okay, you can't really use that if you apply a sine wave, but in this case we are not using it. So, are you saying this as a method of testing the nonlinearity? No, because in this case, I mean, how do you apply a sine wave? So, what happens is, okay, yeah, it is true. In the ideal case, that's one of the ways you test it. But let's say the spectral density of whatever you are transmitting looks something like this. Because of nonlinearity, you can have some parts will intermodulate and fall onto some other parts, and the shape will not be maintained. That's all. And actually, that itself is not the problem. Here, the nonlinearity, the ISI can become nonlinear. The interference to one symbol from the previous symbol can somehow be non-linearly related, in which case it cannot be removed by a linear equalizer. That is the main problem. If you can relate the intersymbol interference as a transfer function of a filter, then you can undo it with another filter. Whereas if it is something non-linearly related, you can't remove that. Okay. So it's always a good idea to minimize the tail node capacitance of the differential pair. And of course, this problem gets worse as you go to higher and higher speeds, because this V, let's say, is the same, but C dV by dt increases in magnitude as the time scale compresses. Okay. So that's I mean, you realize switching coefficients, and you realize coefficients which can be switched to different values. There are different ways of doing that. You can choose any of them. But if you are working at high speeds, minimizing the tail known capacitance may be one of the things you want to keep in mind. In that case, you keep the differential pair itself clean and compact, and you switch on the bias reference side. So that's pretty much about the design of the transmit equalizer. We have a number of taps, number of differential pairs to realize each coefficient, and the coefficient weights can be changed by changing the tail current. Now there are lots of ways of doing this. You can vary it continuously, you can vary it in steps and so on. So if you can vary it continuously and properly, there is nothing wrong with it. I have just shown how to do it in digital steps. Okay. No, it's not just the settling, right? Because the exact waveform matters to the spectrum that you are transmitting through the channel. Okay. Because what goes into the channel is a continuous time signal. So if that has some nonlinearities, it can affect the output. Okay. So if you think of the output as the ideal signal, which is linearly related to the input bits and some nonlinear error, and you pass it through this channel, which is a filter. Now the filter will delay things and maybe delay the two signals differently and so on. So let's say if you didn't have the nonlinear part, that would simply create intersymbol interference, which was a linear effect of the previous bits and the following bits. Now that extra interference can also come from the nonlinear error. Okay, that's because it's not that the channel will simply delay the signal or something. So even if you have a small nonlinear part, if it has a large enough amplitude, it can get delayed and then interfere with some other bit. Okay, and that interference becomes nonlinear, and that you cannot undo using a linear filter. Okay. So it's not just the final settled value that matters. So and there are other techniques of realizing transmit equalization, which are more analog techniques. Meaning this way we implemented it very conveniently in digital form. Meaning we know that with a flip flop we can realize ideal delays for a digital signal, and we sum the delayed signals using different weights, and we get an FIR filter. Okay. Now we can also do it in an analog way. We can try to make analog filters in the transmitter. So that approach has kind of fallen out of favor now because this is so convenient to realize. But let's say I had to make it in a continuous time way. What would I do? I had to make a continuous time type of filter in the transmitter, which will undo the intersymbol interference because of low pass filtering of the channel. What is an approach that I could take? And let me also say that we will be driving similar channels. That is, channel is basically a differential pair of wires or a transmission line terminated on both sides. So if you didn't need any equalization, this is the transmitter you would use. Now if I want equalization, I want to add something to this, or I want to change the circuit in some way. One way I already showed, that was to add different taps, and each differential pair is driven by delayed voltages, okay, delayed bits. Now I don't want to do that. I don't want to use flip flops. Like, what are the other ways I could realize equalization? And equalization essentially here is high pass filtering, right? Because the channels are low pass, you have to realize a high pass filter. What are some ways that I could do that? Oh, no, we can't play around with the transmission line, because that's a channel that you have to plug into. That's it. So let's say this is the boundary of the chip, and whatever you have to do should be inside here. It can also be inside the receiver chip, but let's now stick to the transmitter side. What is the idea behind equalization? So let's say I had a 2-tap, FIR filter, which was basically 1 minus, let's say, 0.5 Z inverse. So let's say I realized it using the method that we discussed in the last few classes. What is the waveform that I would get for a step? What is the waveform I would get from this for a step? What is the step response of this? So it will become 1.5 here, and it will stay that way for one symbol period, right? Is this clear or no? And it becomes 0.5, not 1. Okay. And the DC gain of this is 0.5. So if you look at it in the discrete domain, if you apply a sequence of ones followed by a sequence of zeros, what you would get would be 1 minus Z inverse. That's it, right? So you would 1 minus half Z inverse. So I think I should take this to be basically -1 to 1 transition. Okay. So let me take it from -1 to 1. Let me scratch out all of this. 1 minus 0.5 Z inverse, and then I have negative samples, and then it becomes positive. So if there was a long sequence of -1s, it would have settled to minus 0.5, and here it becomes plus 1.5, and after that it becomes half. Okay. And if you look at the waveform out of the transmitter, it will look something similar. Okay. So this is what you get out of the equalizer. So how does this help you? There are various ways of thinking about it. I know that this already is a high pass response, so it compensates the low pass response of the channel. Okay. So another way to think about it is, let's say I had a first order RC filter to which I am passing this. Okay. So if I had this step, it would rise up as an exponential slowly. Now by introducing this overshoot, what I am doing is I am kind of aiming high during this period, right? So if I applied a larger step, it would start off with something of this sort. So I initially apply a larger step and then step back to some smaller value. So what happens is it will start following this, and then it may do something of this sort. So it starts by trying to follow a much larger value and then falls back to the smaller value. So when you compare it to the smaller value, it looks like it has gone faster. That is another way of thinking about equalization. Okay. So if you apply a step to a low pass channel, it will respond. If it's a first order low pass, it will respond as an exponential and quite slowly, let's say. But if you had applied a larger step, it would have responded like this. So when you want to apply the smaller step, you go high and then come back after some time. So it will do something of this sort. So which is much faster than this. This is another like time domain way of thinking of high pass filtering. Okay, it's exactly the same process, but so it's convenient to think about. So it's something similar that you need to do if you want to realize an analog equalizer. So you can think in frequency domain, time domain, whatever you want, right? And that's how you normally come up with circuits also. After that, you do the thorough analysis and prove that it does work in all cases. So that's effectively what I want. I want some kind of overshoot near the step. Is this clear? So what do I do? Now I don't want this FIR like different differential pairs with delayed inputs and all of that. I want a more continuous time analog approach of realizing the equalizer. And I also said effectively what I'm doing when I'm equalizing is creating an overshoot. If you have more taps, you will create more complicated responses. If you have a precursor tap, you will have an undershoot. And then if you have more taps, you may do something of this sort. Okay. But effectively, the idea is to, whenever there is a step, you make the amplitude of the step larger than what you need it to be. Okay. That way, it will rise faster. So how can I make the continuous time equalizer? Is the question clear? Yeah, but that's the same thing, right? If we have digital data, whether you have a sample and hold or a D flip-flop, it's the same thing, because D flip-flop is a sample and hold that works only for digital signals. Okay? If you apply a different amplitude, it will still hold the same amplitude. That's the only problem. So that's why you can't use it for analog values. But for a digital signal, a sample and hold and a flip-flop are practically the same. Yeah, I want to now, this is only in the transmitter side, and I don't want to use this flip-flop or FIR based approach. What else can I use? So let's say I just want to create a signal like this. Whenever I have a step, let's say this is the transition of the bits. It was -1 and then it becomes 1. So clearly if I put this, I know that the channel will be too slow to respond. So I want to overshoot this a little bit and then come back this way. So what can I do to get some response like that? So have you seen step responses which look like that? So second order system which has some peaking in the frequency response, basically it's an underdamped second order system may do that. Okay, that's one possibility. What else? Yeah, that I mean sometimes you can use that, because you know that if you make a second order low pass, let's say low pass response, you can have something that is maximally flat, which shows you some ringing in the time domain. You can have a large amount of peaking, which will have a lot of ringing in the time domain. Okay. Or you can have overdamped stuff, which will be more sluggish, which is anyway you don't want for this. So you can try to introduce peaking in the frequency response. What else? What else can you do? Can you do it with a first order system? Which is continuous time equalizer? Yeah. No, I mean, it's a sort of continuous time implementation of, the response is discrete time, right? Meaning the response is, the time domain is quantized into steps of Ts. Okay. So in that way, you can think of it as a discrete time transfer function. Okay. What I mean by discrete time transfer function is some transfer function that repeats every sampling frequency. Okay. So that is what I mean by that. But instead of Z inverse, instead of working with samples, you work with the whole waveform, but then you have e to the minus s times Ts here. That is a continuous time implementation of the same FIR response. So here I am talking about a totally analog filter. Series RC will do it. What will it do? Where will I put a series RC? So what is the circuit I will use? So is this the circuit you are talking about? So what is the step response of this? So the step response of this is, if you apply a step, it will go up, it will go up and then fall down. Okay. So, but of course I don't want it to fall down to 0. So what do I do? So can I or can I not create such an overshooting response for the first order system? That was the question. But what's the difference? Anything you can realize with RL, I can realize with RC. But that's okay. What's the RL circuit that you will use? So you just think about this. This starts from 0 and goes back to 0. But I don't want it to go from, go all the way to 0, right? Because I have to have some steady state value for the bit. Otherwise I won't be able to detect it. So add another capacitor in parallel with which one? So what will this do? What will be the response of this? Yeah, it will, the response of this will be actually a smaller version of the same thing. So how will I create something that if I apply a step, it will overshoot but then go back to not the 0 value. Series resistance where? See, if you add anything in series, if you have a series capacitor, it will block DC. If you have a long, oh, you mean you want to do this? So you can't, once you have a series capacitor, if you have a long string of ones, the output will eventually discharge to 0. Okay. Because the DC gain of something like this is definitely 0, isn't it? So what you want to do is, this is effectively the response that you want to get. So no, I mean, I don't mean the two resistances are equal. So what will be the response to this of a step, of a unit step? I apply a unit step. What is this response? First it will raise to 1. Because of the capacitor is initially discharged, let's say, it will have to rise up to 1. Then, what will be the steady state value? R2 by R1 plus R2. So it will do this. So with a first order response, you can get something of this sort. This will be a first order equalizer, of course. And what does the frequency domain, what does the response look like in the frequency domain? Should it look high pass or low pass? In one way or the other, it has to be high pass, right? That's why it's giving you some response like this. So what does the response look like? I want mod h of f versus f. What is it for low frequencies? R2 by R1 plus R2. And what is it for high frequencies? So how many poles or zeros does it have? Just 1 0. No poles. 1 0 and 1 pole. So where is the 0 and where is the pole? See, I mean, it's a first order response. The low frequency gain is this. The high frequency gain is what? 1, right? So the high frequency gain is 1. So somewhere it has to go from here to there. And it's a first order response. So it will have to do it where? It will have to do it at the rate of 20 dB per decade. So where is the 0 and where is the pole? 0 is at, so this is actually 1 over 2 pi R1C if I plot it on the f axis. And where is the pole? So if you ground this, you have R1 and R2 in parallel with C. That's what gives you the pole. So if your R1C is of the right value, I mean if your C and R1 and R2 are the right values, this boost will be where the channel is attenuating. Okay, and that has to be within let's say Fs by 2. That is the rate of transmission divided by 2. So that's where you want the boost also, right? So before we said that to have faithful transmission, we should preserve the frequencies up to roughly Fs by 2. So you should arrange it so that this boost occurs within that. So once you have that, then you will have equalization with something like this. Now this is some passive circuit. I want an active driver which will realize some response like this. So think about how to do that. Okay. Because I still want the transmitter to look something of this sort. I have to be able to drive a differential transmission line with some amplitude. Okay. So this was used, but because the other one is so easy to implement digitally, it is used more frequently, but maybe there is some occasion to use something like this. This circuit can be simpler than the other one. You don't need flip-flops and stuff like that. Okay, we'll stop here. So let's think about how to make the same, essentially the same response. So let's say a single zero and a single pole, that type of response, but with a differential pair driver which can drive the driver transmission line.